Hello, everyone. Welcome back to a new episode of Skin to It, your guide to healthy skin.
I'm Marlo, fashion stylist and beauty enthusiast.
And I'm Dr. Sandy Skotnicki, your trusted dermatologist.
Today, we're diving into an exciting topic.
We're going to break down everything you need to know about regenerative medicine with Dr. Drew Taylor from Acorn Biolabs to help you care for your skin like a pro.
So grab your notepads and let's get skin to it.
So today we have a really special episode. We're actually not in our traditional area that we record. We're in Acorn Biolabs, which is, I'm realizing, in the very lower levels of the UHN hospital. And we are with Biolabs. It's a company pioneering regenerative medicine. And we're going to take a deep dive into skincare, anti-aging, and the mind-blowing potential of preserving one's own cells for future use. And I really took a deep dive on the research here because I just absolutely loved it and learned a lot. And I also realized how much I love science and medicine. And we have a very special guest for this conversation.
Thank you, Sandy. Yes, today we're joined by Dr. Drew Taylor, the CEO of Acorn Biolabs. Dr. Drew Taylor is a leader in regenerative medicine and co-founder of Acorn Biolabs, dedicated to making stem cell banking accessible for future therapies. His passion for regenerative medicine began in 7th grade after witnessing a knee replacement surgery, where a surgeon predicted the patients would one day heal using their own cells, a vision that shaped his career. Balancing science and sports, Drew earned a PhD in biomedical engineering from the University of Toronto while pitching professionally. A career-ending injury shifted his focus fully to medicine, leading him to work with Mount Sinai Hospital's bioengineering of skeletal tissues team, and later as chief science officer at Epic Capital Management. In 2017, he co-founded Acorn Biolabs to offer non-invasive cell banking, empowering people to preserve their own cells for future regenerative treatments. Through Acorn, Drew is bridging the gap between cutting-edge science and everyday healthcare, helping individuals take control of their longevity and health. Whew. Dr. Taylor, thank you for inviting us to your amazing
Yes, thank you so much for having us here.
And taking the time for this interview.
Thank you so much for obviously having me on, and that was quite the intro.
Yeah, we wanted to make sure we got all of it. And actually, on the next point, what we have a little bit of a tradition is we like people to really, tell us about your journey of getting here, how you're a professional athlete, and now you're like, running a tech bio company. And I have two questions for you. Did your experience as an athlete, I was an athlete as well, injuries, physical wear, must have sparked some of your interest in regenerative health? And then can you really define for our listeners regenerative medicine?
So let's do the easy one. Regenerative medicine, as the best way that I would be able to define it, is essentially the part of science and medicine that is leveraging our own cells and tissues to restore function in our bodies that unfortunately are diminished because of age or disease.
That's a great definition.
And in that way, bringing us back to a previous state of performance.
So it's no longer kind of, sci-fi. It's here. It's actually here.
It is here.
Yeah.
Yeah.
And then your journey as a professional athlete to a biotech magnet.
Yeah, well, I was pretty lucky. I had some great people that shaped my life and the path I was on. So my dad being a huge one, as well as my mother. So she was a nurse and he was a physician. But my dad also played professional baseball as well.
Oh wow!
And he had
really followed his
phenomenal
footsteps.
career. Yeah, so he's actually a very celebrated Canadian athlete. He was on the 1964 World Championship Cardinals and the 1969 World Series champion Mets.
I didn't know that. So cool.
And then he went back to medical school at University of Toronto right here. And I think his first year of medical school, he was 35, 36.
So he's older, yeah.
Well, he had a 10-year baseball career and then went back. And then he became the team physician for the Blue Jays, ran the sports injury clinic at Mount Sinai, and had a family practice up at Yonge and St. Clair. So
actually, we have an interesting story there. Your husband.
My husband was Drew's father's patient until he retired.
There you go.
So there you go.
Did you do a good job?
Excellent. He was actually very sad when your father retired.
I think a few people were. My dad was very special. The one thing I learned from him in healthcare is he was exceptional at listening to patients and giving them the time that they needed. I think it's tough right now, right? I mean, healthcare systems are definitely stretched. and we don't always have as much time as we want to give to an individual. And it becomes a very delicate balance of how much time you can devote to that. And so for my dad, he was somebody that would always make the sacrifice of efficiency to make sure that patients got what they needed.
Is your dad still with us?
He is still with us.
So he must be completely jazzed about this whole thing.
I mean, he was following it along. You know, he's getting older.
Yeah.
Right. So I think, you know, he's at a period of time where he's not diving into the science and things like that. But he was following along all the way through. And so he's been pretty excited about the work. He definitely was a big believer that one of the new pillars in healthcare will be delivered by our stem cells.
And regenerative medicine. Has he given you one thing to take, like one good piece of advice that you would?
Well, we're probably jumping ahead in the timeline story, but I did follow in his footsteps in both paths.
Right.
So I was going to go down and become a physician.
Right.
I went to the University of Michigan, and I ended up studying pre-med biology. Ended up graduating a little bit early while I was still playing baseball there. So I did a master's in molecular cell developmental biology, and then applied to medical school and was accepted. And at the same time was offered a contract with the Blue Jays.
Wow, so cool.
Yeah. So it was a tough decision to make there.
Yeah.
But I only had, you know, a limited opportunity to play baseball because, you know, time marches on.
Yeah.
And I felt like, based on my dad's example, I could go back and do medical school one day. But not wanting to lose momentum, I talked to the dean, and they suggested, look, you can't do medical school at the same time, but maybe explore PhD. It's a much more flexible program from a time perspective. You're not like beholden to patient experiences and things. So I applied to PhD programs very quickly, was accepted at University of Toronto, so jumped on that opportunity. And I did my PhD in the off seasons while playing in the minor leagues for the Blue Jays.
Right.
Didn't last forever though.
Right.
And so I ended up having a arm injury.
Right.
Needed some regenerative medicine back then. And tore my labrum and my supraspinatus, which ended up being the kind of slow decline of my career. Still played for a handful of years after that, and you know, a few years with the Blue Jays and then one with the Phillies. But inevitably I came home, right? So we all get told at some point that we can't keep playing the good game. And coming home was a very emotional moment for me, right? This was the culmination of my dream of becoming a professional baseball player at the major league level coming to an end. Yeah. And so talking to my dad, he could see how I was in a bit of torment over it. And he had a very poignant statement. And this is the piece of advice, to make a long story short, is he said, if I had never picked up a baseball, the world would have been the same.
Right.
But the amount of people that I've been able to affect by becoming a physician has changed a lot of lives. Yeah,
that's great.
That's beautiful.
I'd love to meet him. Well, on that note, I mean, talking about changing the world, so let's get into part of why we're here. My first question, and I'm going to try not to, you know, it's just so exciting for me. So really, before we get into your lab and banking people's cells, let's talk about one of the biggest breakthroughs in modern medicine, an induced pluripotent stem cell. And I'm going to let you talk about what that means. But this technology, for the listeners that don't know, and I don't know how, I didn't know. So in 2012, the Nobel Prize in medicine went to Shiina Yamanaka and Sir John Gurdon for proving that you could take an adult cell that was fully developed, like skin or blood, and reprogram it back to a stem cell state. So Drew, my question to you is, can you explain to our listeners what a stem cell is, why they're so important, and how this new discovery of turning a normal developed cell like a hair follicle back into a stem cell can really change lives, just like your dad said?
Absolutely. So I think the first thing is defining like cells in general, right? And
Thank you very much.
Good place to start. Well, you're the cell biologist.
Yes.
Not all cells are created equal as well, right?
Yeah.
So if we want to think about cells, they're going to fall somewhere on a mountain. And at the very top of that mountain is that magic moment where sperm meets egg, and that cell can become become every cell in the body.
Right.
The bottom of that mountain, around the ring of all the different faces and slopes of that mountain, are different cell types that are final, right? So adult cells that have become what they're going to do and performing: liver, pancreas, skin, you name it, all those different cells. But they're cells that kind of lie halfway up that mountain. And they're still stem cells. They can give rise to a multiple amount of cells, and so we call them multipotent.
Right.
And those cells can become, a number of cells that are on the face of that side of that mountain, right? But they can't wrap around to the other side and become something completely different.
Great analogy.
Yes, thanks. So just for people who don't understand, so when you say cell or stem cell, can you just...
Yeah. So a stem cell, by definition, is essentially a cell that can divide, maintain its stem cell properties with a mother cell, and then produce a daughter cell that can then continue to differentiate into one of those terminal type cells to perform.
It's basically, it can become anything: brain, heart, nerve, pancreas. Right.
So that stem cell at the very top of that mountain can do that. It can roll down any face it wants. But we still call different stem cells in our bodies stem cells, right? And this is why not every stem cell is created equal, that are halfway down that mountain. They've picked a side or a face to start to roll down, and so they can only become a handful.
We actually have a kind of a stem cell in the skin. The base of the epidermis, the basal cell of the epidermis, is continually replacing itself. So that's why we get new skin every 30 days. So basal cells are a quasi stem
They're
cell.
an adult
Yes?
stem cell.
Yeah,
Yes.
there you go.
And then in our hair follicles, we
Same
have
thing.
mesenchymal stem cells.
Right.
And these cells are constantly migrating in and out of that hair follicle to help regenerate tissue when you've got damage or other things, as well as releasing factors that are able to stimulate locally that niche of cells in our skin, as well as the base, the root of our hair follicle to produce keratin.
Okay, so why did you choose then hair follicles? Let's get into hair follicles as opposed to skin cells. And I mean, I guess getting at them or taking them is probably easier. You can just pluck your hair out,
Lots
right?
of them, easy to get at.
So can you take us through that part of the journey, how you decided on that?
So for two reasons, really, that are main is one, you want to choose and have a cell type that can deliver value in its present state, right? So without having to manipulate it. And then secondly, you want a cell that is appropriate or has high survivorship when you do manipulate it. And this is important when we're talking about what you brought up with iPSCs, right? Induced pluripotent stem cells. That practice that won the Nobel Prize was taking one of those cells at the base of that mountain and rolling it back up to the top of the mountain so that it can again become any cell type and roll and pick a new face to roll down. Not every cell in us does a good job of surviving that process or having that process be successful. Okay, we have different efficiencies in cell types. And so what we wanted to do was pick a cell type that is possible to be leveraged today beneficially, and mesenchymal stem cells can deliver a massive amount of benefit through an entire side of that mountain, but also can survive that process of becoming reprogrammed for some of the longer term strategies in regenerative medicine.
Just for our listeners, I know what mesenchymal means. So there's ectoderm, mesenchymal, and endoderm?
Yes. Yeah. So, endoderm, ectoderm. And so mesenchymal is actually, think of it as cartilage, bone, fat.
Right.
That's the trifecta really of
those
cell
types of cells that develop into that type of tissue. And then ectoderm is the skin.
Ectoderm is skin and nervous system.
Yep.
And endoderm is a lot of our internal organs. And things.
Okay. So those are all different cell groups that can go different directions. But a stem cell can go into, like a true top of the mountain, can go into any one of those three.
Correct.
My next thing is, this is what really blew my mind. And I have to say, I knew about what you were doing. I knew a little bit, and I was like, hair follicles, how can a hair follicle be a stem cell? And then I started to really, your paper and on pancreatic induced pluripotent stem cells. So basically, one of the things I wanted to get across to the listeners with this podcast is about skin and regeneration and beauty, but also the science part is, from what you're doing, can change lives in a much bigger way. So from the study that you published, where you took your hair follicle stem cells that you produced, induced stem cells, you showed that you could push it towards pancreatic cells and possibly treat diabetes type 1. So in diabetes, people aren't making insulin, their pancreatic cells are working. And further to that, it may have applications in macular degeneration, which is a disease of the eye where you lose sight. And then the one that really got my juices going was Parkinson's, because Marlo and I have one dear friend, two friends actually, and my aunt that have early Parkinson's. And in our early discussions, you said you maybe even are pushing cells into neurological cells. So my question to you, Drew, is for our listeners, how can your banked cells from hair follicle, and we haven't really even gotten into the whole how you bank them and cryopreserve them, but how can they potentially treat internal disease?
So because of those two ways that we wanted to make sure that we have a cell source that is valuable today and leverageable today, and that are those mesenchymal stem cells that are present in the hair follicle, as well as survive reprogramming, right, to create those iPSCs. One is for delivering value today or in tissues that are closely related to the hair follicle. And so that does include cartilage, bone, adipocytes, fat. It includes a lot of connective tissues. And in fact, the hair follicle has ectodermal lineage within it cells as well. And so you have possibilities in neuronal pathways. The pancreas paper, you're creating endoderm, right? So you have to change the actual fundamental face of the mountain that cell has chosen. So we reprogrammed the cells in that study, and it was led by a fantastic member of our Acorn team, Amatella, as well as collaboration with Mount Sinai Hospital and Dr. Ian Rogers, who's a phenomenal scientist. So this was really a team of people that came together to do this.
Yeah, it was a big study. Yeah.
It was really very exciting for us. And, and it hits close to home because my younger brother is a type 1 diabetic.
Oh.
Which is why it was one of the choices of
targets. Yeah.
Yeah. Ultimately, it wanted to stand as a testament to show that the cells that we're targeting in the hair follicle have the ability to be efficiently reprogrammed and pushed into other lineages.
Wow. So do you think we could make cartilage and things like that and use it for degenerative osteoarthritis at some point?
Okay, so a little inside scoop. We are doing that. We've been able to create cartilage on demand, bone on demand, and fat on demand from the hair follicles we have stored. We have a study going on right now.
Where do I invest? Sorry.
We need an investor relations.
Wow, that's fascinating.
Yeah, we're doing the cartilage work in collaboration with the University of Calgary. And so right now we're testing it in an animal study right now in two ways. One is we actually are leveraging the mesenchymal stem cells that can be isolated from the hair follicle, as well as just capturing the secretome of what is released by those mesenchymal cells.
We're going to get to that. That's interesting. So just for the listener, osteoarthritis is a degenerative disorder where your joints break down, really because you start to lose cartilage. So, and there is absolutely no treatment for it at this point because we can't replace cellular tissue until maybe now.
Can you take us through the cryopreservation process? And I mean, Sandy obviously told me to say that word. I say the freezing. Right, the freezing process. And I guess does the talk about the age of the cell when you capture it, like how that makes a difference to it, and if you can explain that process to us.
So ultimately, what we want to do is bring the cells down to a temperature where there is no more metabolism that's running. Okay, once we stop the metabolism running of those cells, they're literally frozen in time. So your home freezer won't do that. Right. And it creates things like freezer burn. And, you do get slower, but degradation. You have to bring it down really low. And so we actually bring the cells down to negative 310 degrees Fahrenheit or negative 196 degrees Celsius. So it is about 10 degrees warmer than the surface of Pluto. This is very low temperatures, the lowest temperatures that we can get.
That's a great analogy. I like that.
And at that temperature, the cells are not aging anymore. They're frozen in time for you. So essentially, whatever age you are that you end up having your cells collected, you'll forever have part of you that remains that age. That's the idea.
So best to collect them early.
Well, actually, that's my next question, because from your studies and your research, which I found fascinating, two things, the difference between men and women there, but also it was hinted in your pancreatic study that it didn't matter that much about the age. Like, so if you're 70, or if let's say you're 60, because, in your 60s, that's when some of these degenerative diseases start to happen, Parkinson's and osteoarthritis. You're not too old. So you can get your hair collected because the the outgrowth of those cells was in your study was just as powerful as younger hair follicles, correct?
That is correct, right?
Yeah.
And so in this instance, absolutely, right?
Okay.
There's opportunities. Now, I do think that there's value in banking as early as possible.
Sure,
As
of
early
course.
as
Yeah.
possible.
Yeah.
But one of the big efforts that we've been making as a company is to make sure that patients have the opportunity to leverage and derive value regardless of what age they're able to do
What age
this.
they're? Yeah, I think that's an important point for the listener too. Like you might be sitting there going, "Okay, I want to do this, but I'm 50," or
We have
and
people that are in their 80s that have done
right,
this.
yeah, and in the next 10 years, this may completely. We might be from bench to bedside more quickly.
Mhm.
Did you have a question?
And does it matter if certain diseases, like if you already have, let's say, certain diseases or certain issues, does it matter? Like,
It's
do you
not-
want to do it before you start to have these problems, or
It's a good question, actually.
Yeah. So it's a big question, right? And it really gets down to almost like a little bit of a philosophical question too, right? Is the interplay between aging and disease, right? Is aging just the accumulation of multiple diseases moving forward, and ultimately, from that perspective, it doesn't matter really if you are in disease states or not. The best version of yourself that exists is today, because unfortunately, it doesn't matter how many push-ups we did yesterday, we're a day older tomorrow.
Mhm.
So just capturing them as early as possible, regardless of what your health conditions are. Now, because we target the hair follicle, which I think that's the first time we've brought it up so far, but we target the hair follicle, right?
Yes.
Because that is what we have found to be this premium source of cells that is has the combination of all of the factors we've talked about, being reprogrammable, delivering value today, surviving these processes extremely well and being hardy, but also, best of all, from a patient perspective, honestly, pretty easy to get access to.
right?
Yeah.
Yeah. So the hair follicle does have unique things to it. So for instance, we end up having a lot of patients reaching out to us and pursuing the opportunity to bank their cells immediately before, for instance, they go on chemotherapy,
Right.
Because that is going to specifically affect our hair follicles. Interestingly,
Right.
the reason why chemotherapy affects our hair follicles so much is because of the high concentrations of stem cells in our hair
in the
follicles.
follicle. Yeah.
Chemotherapy targets cells that are highly dividing,
Yeah.
including cancers, as well as our stem cells. That's why it makes us feel so sick.
Mhm.
And we lose our hair because of the high concentrations of stem cells in our hair follicles.
An interesting two things I want to add there is, I'm a practicing physician. I see many people who have chemotherapy, they lose their hair and it comes back different. So it comes back curly.
Curly, yeah.
And so, because the stem cell is it's just interesting. It just hit me there. The stem cell is actually being affected. So it's somehow being modified or changed. So the second part, which I found very interesting from your study, and actually just to digress, we didn't say for the listeners when we're targeting, it's not the hair, it's the follicle. So the follicle is the root or the sort of the organ, and that's you don't see. That's when you pluck it, you see that little white thing.
The
That's
bulb.
what you're targeting when you're talking about banking cells. Those are where the cells are. Postmenopausal women, potentially a problem. So for anybody listening, get your cells banked before you get into menopause. Can you
Too
explain
late
that
for
to
us there.
Well, we're not quite down the whole full tube, but yeah.
No,
So
and-
we're getting our hair done today, so we're going to be okay. We're getting it plucked
Gosh.
today.
So we're still working out a lot of these questions, but one of the big things that we want to work on is if there's optimal times for people to do this that, undergo more hormonal changes. For men, it's pretty straightforward, right? If you have androgenic alopecia, there are changes in certain hormones and receptors and things over, with age and progression of that. With women, it's much more complex.
Yeah.
Right? You've got monthly cycles, you've got life cycles, and all of these different moments in time of these swings in hormones can actually affect our cells, a lot. And one of the areas that has come up again and again is hair. And so women have talked about, right? And I'm certainly not an expert in this, but I'm trying to become so that we can actually help target better times to collect. But there are different cycles that women experience based on hormones on hair growth and how fast their hair grows, or if they lose hair temporarily.
Yes.
Yeah.
So what we learned from your wonderful research assistant here that took us on a tour was that you need at least a good 50 follicles in an anagen phase. So for the listener, our hair cycles through phases, right? We have a shed phase, which is a telogen, a growth phase, an anagen, sort of in between one, catagen. So you need a lot of healthy cells in that growth phase when you're plucking for your samples. And a lot of women are in chronic telogen. They're often shedding. Yeah. So that's an interesting thing, and obviously something you're going to be working on more.
Wow.
So, yeah.
Okay. So let's say if I bank my hair follicles today, explain to me, how long am I waiting to use them, and what am I using them for? Like, let's talk restoring my hair, like skin health. Let's talk about what we're using these stem cells for.
So once you have your cells frozen down, and the way we do it by plucking follicles just from the back of the scalp or the occipital region, you have a very low number of nerve endings there. It's the last place that male patients usually go bald.
Yeah.
And so it's usually have great access to hair follicles there, and it's not tough. So my wife and I, we've got 3 young boys at home. All 3 of them have had their hair plucked.
Oh,
and
cool.
None of them complained. So if they can get through it, anybody can.
Right.
It was kind of funny. The older 2, when Jen and I were watching them go through it, they were the only ones that were, saying like, oh, do I have to do this now? And everything. And then, of course, the youngest, who I can't even remember, was probably like 6 at the time, was like, there's no way that I'm not watching my brothers go through this and not getting plucked myself. So he had to march up and jumped onto the seat.
That's great.
So it is, once you have those locked down, we actually separate those into 4 vials for you.
Okay.
So we alquat it or separate into 4 vials and freeze those down independently. We even separate 2 vials into 2 different tanks to provide redundancy at every step of this.
Yeah, he showed us that actually. Yeah.
So when you go to leverage those cells for the first time, one of those vials would be drawn out.
Mm-hmm.
And those cells would then be grown or cultured in the laboratory towards a respective use.
Okay.
The use that is available today is actually leveraging the secretome. So our vision is increasing complexity of how we deliver value to patients leveraging their own cells. And the first wave of that is actually leveraging the stem cells from that patient in the lab to produce high volumes of proteins, growth factors, collagen, elastin, all of these things that are vital for skin and hair health in copious amounts that can then be delivered back to our skin or scalp and replenish those dropping levels.
Wow. And how are they put back on to the skin and the scalp?
Yeah. Typically in combination with a modality that opens up your skin and allows for greater absorption. Our skin our skin protects us. It's a pretty tough layer, and no one can tell this better.
We're getting ahead of ourselves. We're getting ahead of ourselves there. So I wanted to talk about the study you're doing on that. So, but I wanted to just make a point for our listeners. So we're not actually using this. We're not doing stem cells right now, like the pluripotent ones that you might be able to push towards Parkinson's or cartilage from your hair follicles. That's in the future. Mm-hmm. What you're talking about when you're talking about stem cells is the stem cell that's already present in the hair follicle, and you don't have to do anything; it's there already.
Correct.
So there are really 2 paths here. So when you're banking the cells in cryopreservation, those in 10 years when these procedures are further along, then maybe you can use it to treat for Parkinson's or cartilage. So the study that you're doing on your website, the ACN 101, that's really your first bench to bedside application for this procedure, correct?
Yeah, it's not the first study within that, but it's the same. It covers the same application.
Right. So what you're doing, I'm going to get you to explain it, is you're taking those cryopreserved cells that somebody has, and you're not changing the cell, you're not pushing it towards something, you're just taking those frozen cells, and then growing them in large numbers, and then taking a cellular extract from that, which you're calling the secretome, and you're using that over an ablative procedure, a cosmetic procedure. So take us through the study. And by the way, listeners, you can still sign up for this. Yeah. Right. And it's across Canada, multiple sites, I think 25 sites. Yep. Yeah, in the US. So that's where we're using it now.
Yeah, I understand
of it is
that.
Later.
Yeah, I'm getting that. And when you say ablative procedures, just to explain, like microneedling.
So again, we're going to sort of get into that. But when you damage the skin, you're removing skin and it has to regrow. So your whole purpose of this is to show that you can regrow the skin faster once you've damaged it, correct?
Yeah, and actually bring out a greater skin quality.
Oh, right.
So we're tracking the skin quality as well because we're reinfusing essentially all of these essential molecules and growth factors and collagens and elastin back to the tissue.
Wow.
Right. Would you say the secretome, how does it differ from an exosome? And just to define exosome for the listeners, so these are like cells communicate, and you're the cell biologist, but they communicate to each other with these little packets of information. That's the exosome. How does your cellular extract from your hair follicle,
Great question.
Yeah.
So exosomes is a hot topic right now, especially in the world of aesthetic medicine.
Yeah.
An exosome is essentially a package that is released by cells. Almost every cell in our body releases exosomes, but our stem cells release much higher numbers of them, and typically with better contents.
Okay.
But these packages can contain a number of different things. Growth factors, molecular cues, genetic material, things that are going to help, deliver messages or cues to other local cells, or things that are going to help them accomplish their goals, like growth factors and other things.
Right.
The surface of the exosomes is the same as the surface of our cells, phospholipid bilayer.
Yeah.
So when they actually hit another cell, they release their contents into that cell. Those bilayers merge.
Right.
If you think of exosomes as like Amazon Prime delivery system, it would be as if Amazon Prime not only delivered the package to your door, but actually inside your house, and then unboxed it for you.
Wonderful.
Yeah. But the thing is, you better want what's inside that package inside your cell, because it's getting there no matter what.
Ah, good point. So how does your secretome from your cellular extract differ?
The exosome is a part. Exosomes are part of secretome. Okay. The secretome is inclusive to the entire contents that are secreted by these cells.
Okay.
And so when we target the stem cells in our hair follicle and capture that secretome, you end up getting exosomes that have their own contents. You end up getting growth factors that are outside of these exosomes, mRNA and other genetic cues that are outside of those exosomes, as well as large macromolecular structures like collagens, elastins, matrix molecules that typically, depending on size, are not going to be located inside exosomes. So you get that entire package.
And the one other thing you get is it's personalized, because with exosomes right now, you're getting it from major labs that are producing from cell colonies, cell cultures, but this is your own stuff.
This is your own stuff. And
Can you explain that a little bit? Just to read.
This is one of my favorite topics.
Yeah.
I believe that the greatest value and safety that we can deliver to patients is to use their own genetic material and their own cells on themselves. And this is what is autologous, right?
Yeah.
So from yourself to yourself. Using a donor is called allogenic.
Yep.
And so this is something that I'm fairly passionate about. There's been multiple animal studies where we can actually take histology and look at contents in skin healing and rejuvenation, where it has been shown that animals in their wound healing pathways respond better to their own materials given to them than from a donor animal. But on top of that, in any other scenario, when we're thinking of delivering, some of the initial ways that we are delivering regenerative medicine, like organ transplant and things, or stem cell transplant for leukemia patients and things, we're suppressing their immune system so that those donor cells that we're delivering don't attack the host, or we don't attack them.
So again, just to reiterate for anyone who's listening, your whole procedure is using someone's own hair follicle, own cells, own extracts on themselves, rather than coming. Yeah, because there's avenues to get cellular material from other sources, but this is your own. So actually, the corollary question, like I do a lot of microneedling in my office for hair loss. So they come in, we microneedle them, we take their plasma, and then we get their PRP, which is plasma-rich protein, and we put it over the follicles. Why? I think it would be a great study. Maybe you probably were thinking about doing it, to do the secretome from someone's own personal hair follicle extract and put it over those microneedles.
That is part of ACN 101.
Yeah, it is part of it.
It's one of the
I didn't see that.
Yeah.
Okay.
And it's interesting because the preclinicals that we did is we took a group of patients and we created their hair follicle secretome for them and drew their PRP, and we compared.
I was going to ask, did you compare?
We did, yeah. And so we have up to 34 times higher levels of essential growth factors and molecules.
Makes sense. Yeah, because it's actually coming from the hair stem cells.
From what I'm understanding, what Sandy was just saying, we avoid a lot of ethical questions when you're actually using your own stem cells, your own biological material. So obviously that was a big consideration for you. And can you just kind of walk us through that?
Yeah, and I think there's two areas here to dial into, and one is ethics, but the other one is also, I think, just the performance of these products that we're creating allogenically. And from an ethical perspective, our philosophy is when you bank your cells with us, you own the cells. You can do what you want with your cells. That's an interesting question when you're starting to match and look for donors, right? And you have to have patients that are signing off on these things. Now, it's not as much of an issue ethically in North America, because you end up having people, or say Canada and the US, where you've got provisions in place to protect donors. And ultimately they have an informed consent, right? Where they understand that they are giving up part of their cellular material for the potential use in other patients, even if it is for profit in the world of aesthetics. Now, what happens often, though, in other countries where there are less provisions in place and even less regulations on how invasive some of these new technologies can be delivered, is a big part of medical tourism right now, is you have people going to the Caribbean or going to Central and South America, or even overseas, and they are getting access to things that are not approved in North America. And their source is also extremely questionable.
Okay, so let's say I bank my cells. What I'm curious about is, let's say I use them once for a certain, I'm having hair loss and I use it once. I mean, is that then done? Do I have to bank more? Like,
well, do you bank 4 of them, right?
We bank 4, right?
Okay.
And so our goal is when you use that first vial, and so we make efforts to try to recollect cells that have not divided yet. And that's important, because when cells divide, they go through an aging process artificially that's on fast forward.
Right.
So we can recollect part of those cells and freeze them down to try to replenish that vial for you again. And nothing's infinite. This is biology, right? So we will utilize that first vial as much as we can, but we will eventually go to the second and then have to go to the third. And so our vision really is to try to make sure that you've got cells that are available for you to leverage today and continue to dip into those populations, and always keep vials, right, for some of the long-term applications.
Long-term applications, like the ones we talked about, diabetes.
But that being said, there will be a, Joan Rivers out there that wants to do this yearly and is really excited about it, or wants to take a bath in their own secret home. And so they are, unfortunately, or fortunately, they are going to get benefit from it, and but then have to also top up their banked sample.
Right.
And so we have systems in place to essentially track that. And as we know the number of vials that they have remaining, we can reach out to say, look, you need to go in and see your dermatologist or your healthcare provider and top up.
Oh, wow.
So I have 2 questions there. First one is, you sort of mentioned, you're taking a personalized approach presently, but do you see having some of your cellular samples being used for widespread use, and that's not personalized?
Yes, but not soon.
Not soon.
Right. And so
is that where the ethical issues come in, or?
So this is a very specific question.
So just to interrupt, do you understand what I'm talking about? Yeah. So like right now, use your own hair follicle for your own process, but another potential avenue for your lab and your viability and growth is to take them and use them for masses of people.
I wouldn't say masses of people necessarily,
not personalized.
Yeah, and I'll try to be as clear as possible with this. Our goal and what we deliver is completely personalized autologous regenerative medicine.
Okay.
In the world of performance aesthetics, injury to tissue, right? So if we're looking at repairing cartilage for an athlete and things, in the world of performance, there really is, in my opinion, no benefit to going allogenic.
Right.
You are not saving a life here.
Right.
You are trying to improve that patient, and their cells will perform for them.
So the studies just show taking your own, which is autologous, are so much better. So why even bother doing the other avenue?
Right. The other avenue comes in a little bit of predicting the future here, which I'm happy to try to do. But there's two avenues to think about how we are going to approach disease in the future. There are genetic causes of disease where we have a gene that is inherent in all of our cells that lead to disease.
Yeah.
Okay. And if we do not have mechanisms in place to correct that for that patient in their own population of cells using technologies like CRISPR, gene editing, then finding a donor that is a very close match, right, and is going to provide the lowest risk for an immune response. It doesn't matter, even if they're family members, you're putting the patient on immunosuppressants, but you'll do that to save a life, right? In the same way that we do this for people that are receiving stem cells for leukemia or people like receiving organ transplants. Even if you get it from your family member, we are crushing down their immune system so they don't reject these cells, and they have to live essentially in isolation, because I'm sure you've seen in your career, like I certainly have seen it. There are patients that succumb to pneumonia, right? Unfortunately, because of their lower immune system.
So that is a great segue into my second part of the question. So I have 3 sons as well. And I did cord blood for all 3 of them because I knew the gentleman at the time, which I'm sure you know him, who started it. So you sort of just answered my question, because I've always thought, okay, I have these cord blood cells are going to be like a hotbed of stem cells that are my kids' own, but I'm mixed in there. So how does that get from bench to bedside? You just sort of just said, right? Like if somebody, like if they have leukemia or they have something that, well, they can use these cord bloods that have been in cryotherapy for a long time, but actually explain to the listener how that might happen.
Right. Cord blood is actually a little complicated. And it's gone through 2 waves of technology kind of eras. The first one targeted exactly cord blood, right? Those cells are predominantly hematopoietic. Okay, so that's one of the lineages that's halfway down the mountain, and it is blood lineage. Hematopoietic stem cells are fragile. They don't expand well in culture. And they're much less efficient. Only recently have we even had any efficiency around it. They're much less efficient at being reprogrammed into iPSCs. So, unfortunately, those cells, the one approved treatment using those cells is to treat leukemia. And on top of that, within the first 18 years of life.
Oh, okay.
And that's not because the cells expire in cryogenics, right? It's actually because we only get a volume of cells because they don't expand. We only get a volume of cells that's big enough to treat a child.
So what I'm hearing is I need to ditch those and get all my kids' hair follicles.
So I've done this. I did the same thing, right? Yeah. So like I said, Jen and I have 3 kids at home. All 3 of them have been banked, right? The older 2 were part of this era that I'm talking about, where cord blood was the only option. Okay. We added a third, right? This has a 8-year gap or whatever. And anyway, he was able to, in this new period, have not only the cord blood banked, but also the cord tissue. And so if you target the cord tissue, which requires a time-consuming dissection process in a laboratory to target the cord tissue or Wharton's jelly, you get mesenchymal cells.
Okay.
So yeah.
Is that happening now?
It's happening now. It's been happening for, I mean, I don't know the exact numbers, but I would estimate around the last 8 or 9 years. But again, like that is how I would suggest it. It's fairly expensive compared to just banking cord blood, but it does give you access to 2 different cell types, right? The mesenchymal cells as well, which have truly emerged as a much more usable cell type, especially in the near term.
Okay, so let's get on to the Don't Die conference. So you were recently attended the Don't Die National Conference with Brian Johnson. For those who don't know, Brian Johnson is a biotech entrepreneur behind Blueprint, the longevity experiment where he's trying to biologically reverse aging. Seems like he kind of has. Yeah. So can you talk to us about that experience?
Yeah, I definitely want to. For the listeners who don't know anything about Brian Johnson, my sons brought him to me. Like, Mom, you know about this guy? And they showed me what he does for his skin. And I was like, oh, it kind of makes sense. So, yeah, give us the goods on that. What was this guy like? What was the conference like?
Yeah, I mean, so let's talk about the conference first. The conference was essentially, and what Brian has really done is bring together a group of people that are extremely passionate about doing everything that they can to live the healthiest version of themselves.
Yep.
And that is an incredible environment to be a part of, because there are people that are motivated and motivating others around them to really take action in their lives. Now, his big kind of slogan is "Don't die."
Don't die.
And that goes beyond the surface value, right? I mean, he's a bit of a philosopher, not a bit of a philosopher. I would say he is a philosopher, and his mindset around "don't die" is really don't let yourself die and don't let others around you die. Do everything in your power to essentially preserve life. And it is intentional. Instead of saying preserve life, it's intentionally worded as don't die, because preserving life can be different for different people.
That's true.
Right?
Yeah.
In times of war, preservation and ethics and different things, if your philosophy is just at its complete base, don't die and don't let others die around you, in many ways, that's a more powerful statement than preserving life.
Okay, so if you can tell us, it's sort of a kind of wrapping up, a final question. If someone really is intrigued about this, wants to do this, wants to future-proof their skin and their hair, and wants to, can you let us know how they can do that today?
Absolutely. So our website is acorn.me. And on there, we have a map and a list of amazing, practitioners across North America that are offering this. You can have your cells banked at any of their locations. Predominantly right now, because the opportunity to leverage those cells for benefit right now in the world of hair and skin is being delivered by dermatologists, plastic surgeons, and then obviously banking side, we've got longevity clinics, wellness clinics, and even GPs that are really interested in delivering this. Those are the bulk of the locations that you'll find on that. You can even even ask your dermatologist or your plastic surgeon whether they carry it.
So on that note, I want to thank you so much for this fascinating conversation, letting us come here and tour your labs, and a real kudos for you for all that you're doing. And I do think I want to bring this into my office, my clinic. We already had a little conversation about that. I recently joined Victoria Park Lab, MediSpa. They're across Canada. I think it would be a great partnership. So I'll definitely talk to them about that. And this is really incredible and mind-blowing, and I just loved it. Thank you so much.
And to our listeners, I'm sure you found this as fascinating as we did. Don't forget to subscribe to Skintowit, follow us on social media, and stay tuned for more conversations on the future of skincare. Please let us know what you thought of today's episode.
If you have any questions or thoughts, send me a message on social at Dr. Sandy Skotnicki. And don't forget, all the links and resources we mentioned are in the show notes.
And if you haven't already, please subscribe and leave us a review. It helps us to bring you the content you love.
Until next time, take care, and we'll see you next week on Skintowit.